Yeah, we're really excited to come on this Unitary Fund Twitch stream today. We really want to reach out to the open source quantum computing community. We're hosting an event, QHack, Quantum Machine Learning Hackathon. It's February 17th to 26th, so it's coming up very, very soon, and we would love for the Unitary Fund community to take part.
Awesome. So, like, what would I do as a part of how long is the hackathon?
It's going to be 10 days of
Okay.
hackathon. We have 3 days of talks with an amazing slate of guest speakers, including Will Zhang of the Unitary Fund. And then during the speakers, it's 3 days. And then 7 days afterwards, we're having a full-fledged hackathon for everyone to take their best shot at coding quantum machine learning problems and show the world what they have.
Awesome. And we have a new guest, our speaker for today, Shahnawaz Ahmed. Who's going to be telling us about QuTiP. Do you want to, I'll let you introduce yourself so we can get going here.
Okay, so just let me know when I can start.
Go for it.
Okay, so hi everyone, this is the first time I'm giving a talk on Twitch. Feels kind of cool. So thanks Sarah for having me and Unitary Fund for inviting me. I'm going to talk about QuTiP. So this is first affiliated project for Unitary Fund, and it's also a very cool software that you can use to simulate quantum physics. So I'm going to start with a nice quote that I found from one of Roger Penrose's interviews from way back, not last year after he won the Nobel Prize. And there's a line where he says, quantum mechanics makes absolutely no sense. Right? But still, we have a lot of technologies that are fueled by quantum mechanics. So we have quantum sensing, the GPS, you have works on some principles of quantum physics, atomic clocks, MRI machines. We have the field of quantum communication, quantum computing, of course, quantum chemistry, and this newly evolving field of quantum machine learning. And Nathan already mentioned about QHack, where there's going to be a lot of interesting projects related to quantum machine learning. So we see that these kind of quantum technologies are being pursued by several different players at various levels. So NASA is investing doing fundamental research. You have research done by IBM, but you have also big universities and organizations, national flagship organizations that are trying to research on new kinds of quantum technologies. So if quantum mechanics makes no sense, and quantum technologies are using quantum physics in a variety of applications, how does one study and simulate quantum physics? So this is going to be the main part of this talk. How do you study and simulate quantum physics if it's so trivial, difficult to understand? My personal journey in the study of quantum physics as a career physicist in training, because I'm a PhD student now, started with QuTiP actually. So I wanted to understand quantum physics better. So during the undergraduate classes, I tried to look for physics simulations that you can do in quantum physics. And what I came across was QuTiP back in, I think, 2014, 2013. So that was my introduction to quantum physics, actually, using code. And I found it very, very useful to understand. But of late, we have also seen a rise in a lot of different kinds of tools. And Will Zhang from Unitary Fund has actually written a nice comment on Nature in 2017. And Nathan and I have written, Nathan Sharma, he's also working at Unitary Fund. So we both wrote a small little blog about it. So what kind of tools can you use to simulate and study quantum physics? And these are tools that are open source nowadays. So why is it really good? It's good because you can use it for education, research, you don't have to pay for it. And then at the level of research, it is enabling fast reproducibility of ideas and results. So let's say you have a new simulation technique and you used it to run experiments and then do something cool. Another research group should not have to spend months or weeks and PhD student or a master's thesis students 6 months of time to reproduce it. So what you can do is if you open source your code, you can enable the whole community to reproduce your techniques, your research, and then make it faster. for the evolution of ideas. So there is this quantum programming ecosystem that's been developed and pushed forward, and Unitary Fund is playing a big part of it through the microgrant. If we have a look at some of these tools, I've collected a few here. QuTiP was their way in 2012. Actually, it started even before that, 2011. And then after that, you can see there's a large bunch of new software that you can use for different kinds of quantum simulations. And of late, a lot of them have started being in Python because it's one of the more easy programming languages to start with. So QuTiP was started actually in the group of Professor Frank Nori in Japan. And at that time, there were a PhD student and a postdoc, Paul, who's now at IBM, and Robert, who started the project. And then, okay, let's see. Yeah, this is better. And then right now we have a current dev team with Boxy, me, NASA, and Alex, and Neil. And you can check out more of the devs on qtip.org/devs. So what does QuTiP do? Do you have a question, Sarah?
Not any yet at the moment. They were just commenting on the bottom part of the presentation being.
Okay, yeah, I noticed that now. I tried to, let's say, keep it a little bigger. Yeah, exactly. So what can QuTiP do? We have a lot of different kinds of quantum software that are available right now. Some are specific to a particular hardware. Some are specific to do some things that are not so multi-purpose or so general. But QuTiP, what it can allow you to do is simulate quantum physics as a whole, and it's being applied at different levels for different kinds of projects. So you can simulate circuit QED, quantum optics, you can simulate how ion traps behave, superconducting circuits, you can study optomechanics, and one of the more important applications I find is to explore fundamental theory and basic concepts. So one of the things that really makes QuTiP so impactful is that it allows you to simulate quantum physics. And then you see that a lot of people are using QuTiP in their actual research. So I think I checked last and saw that there were more than 1,300 citations of QuTiP on Google Scholar. 2020 alone had more than 400 citations, and some of the journals which had papers that use QuTiP for simulations are super high impact journals like Science Advances, Physical Review, Nature Communications, and more. And at the same time, you can see that a lot of the industry behind the scenes is also using QuTiP. So I've noticed that in Qiskit, you have something called QuTiP Lite. And I'm sure at many other places where you want to start simulating something at the level of, basic quantum physics, you can start with QuTiP. And it's no doubt that it has also found some mention in big articles like The Economist writes an article about quantum technologies and mentions QuTiP. In the NumPy paper, you see QuTiP is mentioned as one of these application-specific branches.
If I could interject real quick, first question. Yeah. If you've used QuTiP in the chat, raise your hand. I know I have. I'm pretty sure when I was in grad school, it was kind of just when it was starting, and I had been writing everything myself, in Mathematica, because I was a dev at Mathematica before grad school, and when I found QuTiP, I was just like mind blown because how I learned Python. Wow, that's awesome. Yeah, I was doing quantum optics stuff, so it was just an easy shoe-in. Did I have to figure out how to describe a Wigner distribution? Nope, I could just use the built-in ones. So as just a side interjection, I really love QuTiP, and I would love to see more courses and introductory stuff kind of based on QuTiP, because it's just so easy to express what we are trying to do here, right? And obviously it's useful based on all of the people using it for both research and industry like this. But yeah, anyway, I love QuTiP.
I mean, entry into quantum physics was because of QuTiP. I started, during my undergraduate, I got an internship in Japan, and I found an online advertisement. They were looking for someone to work on QuTiP. So I just wrote to them saying, I'm still a student. Can I work on QuTiP or learn more? And Franco basically gave me an opportunity to pursue my master's thesis in his group. And that's how I kind of started this whole journey. So QuTiP was like a career break for me, actually.
It's really cool how like an open source project like this can, what it can do both for people's careers and for research as a whole. Anyway,
yeah,
I just wanted to put my 2 cents in there
sure.
because I figured a few people in chat may also feel the same. So please continue.
Yeah. So I tried to look a little bit on who is using QuTiP, and these are some of the papers I found. I think this very nice article stabilized gap qubits. Then, if you can read about like very different kinds of projects that are using QuTiP from quantum chemistry. Here, I think it's mostly bosonic systems. Yes, but like superconducting qubits and this super nice Nature paper. So why is this? I mean, QuTiP is kind of like the true representative of what a community can do. And some of the examples that you can find in QuTiP are like out of nowhere, and they are so nice. You have, I found one example, one tutorial written by Ben Bartlett from Stanford. He just out of nowhere wrote a whole lecture on photon scattering, a bunch of notebooks. Then I was searching for other stuff that people have done with QuTiP, and I found something by Soumya Sriram. She was, I think, a master's student working in Fermilab, and she wrote this super nice report about how you can study qubit interactions with multimode cavities using QuTiP. I mean, I've been planning to contact her and just get the code because she has a very nice report on arXiv. It would be amazing if we could get the code and make it a tutorial or a notebook on QuTiP. So, the community really uses it and also gives back. So to make it a little bit more formal and to make sure that we catch people who are really capable of doing something interesting and we get them to QuTiP, we tried participating in Google Summer of Code in 2019, and actually we got some amazing contributions and new people in. So Toxie, he's a QuTiP admin on the QuTiP admin team now. He made a really good module for including noise models in quantum circuits. And we are trying to make it into a new package. I'll talk a little bit more about it. Jake, who's a final year PhD student, I think, he completely rewrote many of the linear algebra structures in QuTiP, made it faster, made it available so that we are not just storing data as compressed, sparse compressed matrices, and we can work with different kinds of data types. Siddham Bissi worked on kind of bridging the gap between QuTiP and things like Qiskit or CERT by having more interoperability of quantum circuits. So, and then we have some more other projects which are not in QuTiP core. I was part of one of them. So then there's also an ecosystem surrounding QuTiP. There are many other people, other softwares that are using QuTiP. For example, TN Contract, a tensor network library, PIX, which was my first paper with Nathan actually, which got a lot of response because it just made simulating some systems extremely easy. Then I made sure that my master's thesis, which became a paper in itself, everything was open sourced in this tool called Matsubara. And then we found other people who are using optical control, for example, interface with QuTiP and use QuTiP to build on something. And what we want to do is now we want to grow this community, and we want to make sure that more and more people, they don't have to start from scratch. They start from a base, which is QuTiP, and then they build on their own software and share it with the community. So the main driving force is that it's open. Anyone can come, be a part of it, suggest ideas. If something is going wrong, they can just say that, okay, this is wrong, you have to change this. And it's very collaborative. So I had a meeting today with the QuTiP admin and the newly formed board. And there are people from everywhere, from Australia, from Japan, from the US. So now, enough tooting the horn. Let's get to the actual meat of this thing. Like, let's see what QuTiP can. If you are a complete newbie, how can you start? And here I'm assuming a little bit of background in quantum physics. So I'm going to directly start with the code and how you can represent things in QuTiP. So I'll talk a little bit about operators, states, density matrices that you can write in QuTiP very easily. The main thing, the core class in QuTiP, this quantum object, how you can do something even more, super operators, and write different kinds of math, and write time-dependent quantum objects, which are actually the next level of the basic quantum object, which was the core in QuTiP. So let's see some of the basics. So if you know a little bit of quantum physics, you know that you have to define some kind of Hamiltonian. You use some operators like sigma z. So in QuTiP, I'm doing a star import here. It's a very bad coding practice. Please don't do it. You should really explicitly write down what you're importing. But here, just for the sake of saving some space, I'm not writing everything that I'm importing. But if you just import whatever you need from QuTiP, so the ones in red are things that got imported, and then you can start writing your code. So if you want to write a Hamiltonian, a sigma z over 2, for example, you can just write it with this function that QuTiP provides. It actually constructs a quantum object, which is a matrix. You can write bosonic creation and destruction operators. You can write a quantum state with any base. Here, it's a qubit because the basis has 2 states. And let's say you can make a superposition of them. So you take 2 state vectors, combine them. And here I'm actually normalizing it properly, but maybe you forgot to normalize. QuTiP has these nice functions that you can just call, and this normalizes whatever your quantum object is. You can then convert this to maybe a density matrix, which represents a mixture of pure quantum states. So this is like super first thing that QuTiP makes extremely easy for you to handle. So once you have these quantum objects, they kind of know a little bit of how to work with each other. So these states and operators, once they're instances of quantum object, you can manipulate them and you can multiply them, and they'll kind of keep track of the size, the shape, the dimensions of the quantum systems that they represent. So for example, you can directly go and initialize a quantum object by just calling the QObject class and supplying a matrix into it. It will construct to something like this quantum object. And then you can manipulate them as standard matrices, and all kinds of valid mathematical operations are well defined. So you can take a destruction operator A, you can take this initial state, you can apply it on it, and you see that it levels, it goes one level down. It's a destroy operation. But then if you do something wrong, you take care of the proper dimensions, QuTiP will know and tell you that, okay, you're trying to have a destruction operator living in a Hilbert space of size 4, but you can't kind of apply it to something which is living in a Hilbert space of size 2. And then these quantum objects have some built-in methods that make your life easier. Like if you want to take a dagger operation, you can just quickly call .dag and it works.
So we have a question from Siddhanth Pai. I'm new to QuTiP. How do I do analytics? Or how do I do analytics? I've only come across numerics in QuTiP such as that. So I think what they're saying is they want to do stuff like they could in Mathematica.
Symbolically.
Yeah, exactly.
Yeah, this is very interesting actually, because today we talked about a module called I think it was Sims, right? But we're trying to get it to be something like QuTiP symbolic. So right now QuTiP is completely focused on numerical things. There's nothing that you can do symbolically. So one of the things that we want to do in future is have this QuTiP symbolic library. And actually there is something that already exists right now, but we have to make kind of SymPy better to get everything in. So we're trying to formulate it as maybe a future project, a Google Summer of Code project, and get it. But right now, there's not anything that you can do analytically in QuTiP.
That would be really cool, though.
Yeah.
I'm looking forward to that too.
Yeah. I mean, Mathematica is nice. I never used Mathematica so much until I needed, someone told me that please give this to me in Mathematica because they didn't want to do anything else. I found it nice, but at the same time, if I can do symbolic things in QuTiP, it will be such a relief.
Absolutely.
Yeah. So let's see. Then, you can go to QuTiP tutorials, and the documentation is very clear. You have a lot of different things that's already well defined for you. So you have, charge operators, momentum, destruction operators, identity matrices, commutators, and so on and so on. And then, this quantum object has a lot of these properties, very nice properties that you can just call. Let's say you want to find eigenstates of some Hamiltonian. You write the Hamiltonian, you just call eigenstates, and it will give you the eigenstates of the Hamiltonian. Let's see, let's move forward then. This is a slide which is a little bit loaded because it's talking about something which is really showing the power of QuTiP. So, besides your simple operations, you also have support for something like super operators. So you have like pre-multiplying and post-multiplying operations that you can do here. And then you have something called the Liouvillean super operator, which is very easy to create in QuTiP. It comes from an open quantum system dynamics that QuTiP makes it easy for simulation. So if you have a closed quantum system, it evolves in a unitary fashion. So you can just work with matrices, unitary matrices, and you would be fine. But if you want to now include noise, how the system interacts with the environment, then you have to go to an open quantum system description of the system. So here's a very nice lecture note if you want to read about open quantum system. The first thing and the first step that you see there is so-called master equation. So you take a density matrix and you simulate its evolution by writing this equation. It's a master equation. So what you are saying here is that the rate of change of your density matrix is basically calculated with this equation. And QuTiP makes it extremely easy to do something like this. Is there a question?
No. I'm
okay.
Yeah. I remember having to calculate some of these for homeworks. And now being like, this would have been a lot easier.
Yeah, exactly. I mean, it's interesting also, like, I used it a little bit, and then when I started writing a new solver, I realized that inside, if you look inside QuTiP, the way that this thing is done is just beautiful. So you have this system, and what you can do is you can convert it in this Liouvillean format, where you take this density matrix, you flatten it out, and then you just write the rate change equation as this super operator called the Liouvillean super operator, which gets applied to your density matrix. So you have this very nice system that you can solve to get the evolution of this density matrix. And here, for example, on the right, I show how to create this in QuTiP. Let's say you have a Hamiltonian H here. You have some collapse operators, which is the Ci, let's say sigma x or sigma y, and you just call the Liouvillean function in QuTiP, which supplies this Hamiltonian and a list of these collapse operators. And it will give you this Liouvillean. And what QuTiP does when it simulates evolution inside is basically calculate the right-hand side of this equation using this simple multiplication, for example, and then use some SciPy ODE solver to keep updating it.
Gotcha.
So it's really interesting to see, everything here boils down to calculating this Liouvillean. If you have a really fast way to calculate this right-hand side to do this multiplication, you can just use any SciPy ODE solver to kind of run this evolution. So this is what is happening in many of these solvers.
That's cool.
So, the added advantage of QuTiP is everything is open inside, and you can see and you can also learn things to do. So you may be just, someone who's interested in how exactly to solve this system. You can just go into QuTiP and see.
Nice.
Okay, let's see. So let's continue a little bit on the basics. So now let's say you have like 2 qubits. What do? You have to start thinking about tensor products of 2 Hilbert spaces. And in QuTiP, it's very easy to do this. You have something called a tensor, which is a function, and you can just apply maybe 2 states, 2 Hamiltonians, 2 density matrices, and you can tensor them together. And QuTiP will remember kind of how the structure looks like, so that you can, run evolutions, do multiplications, and stuff like that on these tensor spaces. One of the places where it's really heavily used is if you have a multipartite system, which is like 2 or 3 qubits, for example, then you need to use something like this. And if you have something like a cavity or a resonator interacting with a qubit, which is the James Cummings model, you also need something like that. And in QuTiP, what you can do is you can write it as simple as you write a system Hamiltonian, let's say sigma z over 2, and you write, your cavity Hamiltonian, which is, let's say, a resonator with five levels, so Fock level 5. And then you just compile them together as a tensor. And this works. This is your combined system Hamiltonian, which is the tensor product of it. So what you could also do is you could take Liouvilleans and make them a super tensor. So a Liouvillean is already super operator, and you can tensor two Liouvillean spaces together with this super tensor operator. So all this machinery exists. I think these are some of the lesser used functionalities of QuTiP, but they are extremely useful in some projects. So a little bit more advanced than that, and this is a fairly recent addition to QuTiP, is this QObj Evo. So what if you have quantum objects that are time dependent? So before, if you had time dependent problems, what QuTiP used to do is you write the time independent part and you write the time dependence as some kind of function or something like that. So Eric, who's a core developer, he kind of created this quantum object Evo, so that you can represent operators, quantum objects of this format, where AK is some quantum object like sigma x or sigma z maybe, and fk of t is some function. So if you have like a Hamiltonian where you're trying to write a driven system where the drive is kind of a random function which gives the pulses, and the operator is sigma z or sigma x, you can just write it like this. You write a cosine function, for example, which takes in a time and some arguments that you might need to use. And you have this functional form of QObj Evo, where you give the dimension. And this is a new class in QuTiP, which enumerates dimensions. And you basically write the operator and the function that should be called as a time-dependent function here. And then what you can do is you can use this function form as just any other function. So if you call it with 2, it runs it for t equals 2 and then gives you what the quantum object. So again, you never would need to use this directly because these are inside the solvers, but they are super cool if you want to do something custom. Okay, so we now understand a little bit about how to develop, how to write, different kinds of quantum objects, operators, superoperators, Hamiltonians. The next thing is dynamics, and this is where QuTiP power comes in. You really can simulate dynamics at a very fundamental quantum physics level with QuTiP. So it's not just that you have a quantum circuit, you apply a unitary and change one quantum state to another. You can just really go in and simulate quantum physics by evolving the Schrodinger equation from master equation, for example. So this actually is one of my favorite slides because it just shows that you need like 4 lines to write a simulation or run a simulation in QuTiP. So let's say you have this master equation that represents an open quantum system, maybe a qubit interacting with something. It's an, and you have the qubit Hamiltonian is a sigma z, and you have the collapse operators, which in some sense is representing the openness of the system and this interaction with this environment. And you have, let's say, a sigma x, which is a collapse operator. You basically just need to define these two, tell how long you want the simulation to run, and call this master equation solver with your Hamiltonian and initial state or density matrix that we have defined before, and the collapse operators. It just runs. And once you have this result object, what you can do is you can find the expectation value of any other operator on a series of the states that you have on this result object and plot them. And it's as simple as that to simulate the dynamics of a quantum system.
That is really, really cool. Like, so cool. Although I would rather I was trying to make a joke about me solve or you solve, but I'm not very good at I haven't had enough coffee yet this morning. I feel like that would be the kind of joke I would like write on the homework, right before I turn it in, like where you're trying to like, I'm not sure I got this all the way finished, but Yeah.
Don't use me solve, you solve it.
Yeah, exactly.
It's an amazing sanity check, even when you're doing homework, right? Like there's a lot where like I do this, and you particularly write, how they should evolve and things like that. And then I'm not sure if this is correct. Let's just run it, and it gives the sense of like, oh, okay, everything works fine if QuTiP says so. I mean, one of the other things is QuTiP is very heavily tested for different scenarios, different cases. So there's a high level of quality testing that goes on, because it's been used in actual real science, and it's not that if you make a mistake now you get a bad grade. You really screw up a lot of physics research. So it's a little trustworthy also, so I like it that way.
Oh yeah, like regardless, it's a great sanity check. Nathan says num collapse equals 1 ? I don't know what that means.
So I mean, it should tell you that the number of collapse operators is 1. I think it's a small bug because I don't give a comma here. I should fix it.
Chat file the bug report.
Yeah, because it feels like I mean, I just ran it and then I saw that it says num collapse 0, and then I ran it with 2, and then it says 2. So I realized maybe it's a bug because there's not a comma here. But yeah, I mean, this is what it is. You try it up, and someone will come and say, you guys made a boo-boo here, let's fix this. And they can come and fix it.
Yeah, we do need a Twitch GitHub issues plugin. I will put a link to the repo though real quick in case anybody wants to file this.
Yeah, that'd be great. So I tried to actually include maybe some other solvers, but I really didn't think that I would have the time to discuss everything. So the interesting thing is that you have so many different solvers, so many different situations, that all you need to do is, once you have your system defined, change mesolve to mcsolve or rcsolve or sscsolve, and then it uses that particular solver to solve your problem. And each solver, of course, has their own set of parameters, but the basic structure remains the same. So it's very easy to port to other solvers and try out different.
So Andrea was asking what library is used for solving the differential equations.
Yes, it's SciPy int in the backend.
Gotcha.
And also a lot of custom C code that people at QuTiP wrote to make the right-hand side equation computation faster. So in this ODE solving, if you can calculate the right-hand side of the ODE, it's faster, then it's really, really good. So what QuTiP does is it uses Cython to kind of, wrap around C code and do this much faster.
Chat already commented that it looks like mcsolve reports num collapse correctly. Yeah. It's probably just an omission in mesolve.
Okay. It's very interesting. We can have like a lot of these hackathon bug finding sessions maybe. But this is Jake. Yeah, of course. Jake is one of our last year's Google Summer of Code students, and he's actually the one who's writing a lot of the backend that QObject is based on, and basically revamping the whole thing. Like nice. I go in there and I'm like, oh, this is new. And Jake. So yeah, thanks, Jake.
Awesome.
So if you want to now go to time-dependent Hamiltonians, and this is the thing that QuTiP is used most, I think, when you have problems where you want to kind of simulate what's going in your experiment, which kind of pulses should we send to target a particular state, then you can also use QuTiP. And the change that you need to do now is you just need to make your Hamiltonian composite of a static part and a time-dependent part, which is written in the same way as you would write a quantum object, a QObject E. And then, of course, you can just run mesolve with this new Hamiltonian. And this is actually also used in pulse optimization and some of the modules in QuTiP. And we are trying to, branch out into new modules which exploit that QuTiP can solve time-dependent Hamiltonians easily. So apart from just solving the dynamics and allowing you to write your problem, one of the nice things SR already mentioned is visualization tools. So QuTiP has a lot of interesting visualization tools. The most interesting is Blocksphere. So I have a very funny thing, a funny anecdote actually. Nathan Sharma, he finds, when he walks and sees posters and he finds like the QuTiP Blocksphere, and he can recognize that, oh, this is done with QuTiP. And then he can tell, okay, you didn't cite QuTiP, maybe you should cite it because you're using it. So there have been papers where you see the Blocksphere and like, oh, okay, they use QuTiP. And this has become like super cool visualization technique. And we've also used animated Blocksphere, so you can kind of show how your state evolves and so on and so on. And then for example, Sarah, you already mentioned about Wigner functions that you can represent maybe 2D, 3D, other kinds of quasi-probability distributions that you can represent, quantum process tomography matrices, and just hint on plots of your density matrix. And of course, you in the backend, you have this lattice circ library that you can use to visualize quantum circuits. And all of this is just a couple of lines of code. And you can use your evolution, for example, and plot it on a Blocksphere to show how your dynamics evolve. So I'm not going into the code and how to do it. You can check it out. I hope I've given enough incentive just with these pretty pictures.
Chad says QuTiP plus Maya AVI equals best Blocksphere viz out there.
yeah, exactly.
I've definitely used the Blocksphere one for actually doing like single qubit optical tomography. I just used Jupyter Notebook's live updating my basic current estimate for the tomography on the sphere and kind of watched it walk its way to what it was supposed to be in most cases.
Yeah, it's really cool. I think Jupyter allows you to also animate things, and you can just see it there, and it's always cool. Like, it gives this effect when you show it there, like, wow, okay, and it makes it more interesting. Yeah, kudos to the Matplotlib team. Exactly. It's Python scientific ecosystem just blows my mind. It's amazing. Like, you'd find things in there when you start looking that are like, wow, this is exactly what I needed. And some savior on the internet on Stack Overflow, like, did it for you. So it's really cool. So so let's see some of the new things that have been added. So one of the things that really, I think, is getting attention is these noise models that Boxy added. So Boxy was a GSOC student last year, Google Code student last year, and he did this amazing thing where, I'll talk about it in detail in the next few slides. And of course, Jake is here, and Jake completely reworked the data structures behind QObj. And then there was one more project which didn't actually become part of QuTiP core because we needed to kind of make it work with Google JAX. So what we try to do is we try to take auto differentiation and say that if you write a QuTiP function, can you apply any auto differentiation tool to take gradients based on something and optimize? And we found some really cool applications of this. So you could learn unitaries, you could learn gates that you need to target something. There's a paper by Seth Lloyd about learning unitaries by using gradient descent, and we could implement it in just a couple of lines of code. So we had to kind of rewrite some parts of QuTiP using JAX, and it works. But after what Jake did, and kind of reworking the data structures behind QObj, if we are able to somehow make JAX arrays work directly in the QuTiP backend, it's like a whole new thing that opens up that we can apply auto differentiation on QuTiP. So, hi from BITS Goa. That's one of that's my undergraduate school from India. So, hey. Okay, let's see. Kudos to Siddhant Saraugi for his work on QIP module in GSOC. Yes, I think I mentioned it in the beginning. So Siddhant is basically, what he's doing is he's bridging the gap between QuTiP and other tools and continuing on Boxy's project. So what Boxy did was he created kind of a whole new module out there in QIP, which
where you can define your own device. So here I give a device which we call this optimal pulse processor, but you can define your own processor. Let's say you're working with Rydberg atoms, and you know some specific things about Rydberg atoms, and you want to run your quantum circuit on them. What you can do is you can make a new device called, let's say, a Rydberg atom device, and we kind of separated the quantum circuit part from this hardware device level part. So here, for example, let's say you have this device, this optimal pulse processor, which has maybe, let's say, n qubits or n level systems, and you have maybe a drift Hamiltonian that is sigma x. So therein you can basically create, your processor, your simulator, or whatever you want to call it, and then you can control Hamiltonian. So let's say you have a control Hamiltonian sigma x. So then, here it should be one QC. Let's say you make your own quantum circuit, for example, and now because of Siddhant, we can also import quantum circuits maybe from Quasar. So you have a quantum circuit, for example. What you can do now is you can use this, load up your quantum circuit and just run this. And this processor, using this processor, you can also kind of get optimal pulses that you would need to maybe target something or run this circuit. And you can, for example, noises like T1, T2 that is characteristic of, let's say, a superconducting qubit. If you write like a superconducting qubit processor and kind of see how the simulation would work with a certain level of noise. So it's done this really nice job of making QIP connect with QuTiP and allowing realistic simulations of quantum software without really making it hardware specific or giving the flexibility that anyone can come in and propose a new hardware with all the quirks, and then it works. So this is a really cool project by Boxy. Jake, I mean, there's not a lot of pictures here about Jake's project because Jake has done something in the core, which...
Oh no, I heard the Skype dupe. I think I lost Shahnawaz. Hopefully they'll be back shortly. I'll give like funny elevator music. So who after the talk here is interested in using QuTiP for some of their work or research? Let's join the call here.
I dropped out for
a
couple of seconds. Yeah, I mean, I was connected on the LAN, but I noticed that my Wi-Fi was on, so I guess I was on Wi-Fi and then dropped.
Gotcha. I think you may have to share your screen again.
Okay, yes. Let's see, share screen. Can you see the screen now?
Yes.
Okay, perfect. So, I mean, before what QuTiP was doing was everything was getting stored as a compressed parse row matrix, which was really good for large sizes of quantum objects. But many people started complaining like, I want to simulate maybe 3 qubits, 4 qubits, and then this all the overhead that was going when storing, unraveling with this compressed parse row matrix was creating a lot of lag and overhead and making things slow at small sizes. So Jake came up and had this complete overhaul of the whole thing and wrote a new data layer abstraction. And that makes it possible for other parts of QuTiP not to care about how the data is stored at the lower level. And then you can change and do operations between similar data types. And if things don't work out, what you can also do is you can have this dispatcher which takes care of the proper conversion and make all kinds of things work. So, Jake, do you have to say anything about it more? It's pretty technical, so even I don't get the full nitty-gritties of it at this point. But yeah, I know it's something super cool that's happening and that will allow QuTiP to work at the lower level with many different kinds of data formats. So then let's see what we want for the future. There's already been a lot of talk about control. And what we want to do is we want to make the main QuTiP, the core QuTiP, much lighter and branch out in these sub-modules or independent packages, QuTiP control, QuTiP QIP, QGrad, and also QuTiP symbolic, for example. And one of the incentives for this is we want folks to be able to come to QuTiP and say, hey, look, I made this super cool library about quantum machine learning on QuTiP, powered by QuTiP. And I want it to be part of QuTiP. But maintenance becomes a nightmare there. If you want to put everything in QuTiP core, you have to take care of many dependencies, more tests, and all that. So we want to make it a little bit more flexible that people can come and develop very nice, interesting tools which are surrounding QuTiP. And already we have some very nice, interesting tools around QuTiP that we want to split out. And then what really is something that's long overdue is overhauling the documentation for the entire project. We tried to apply for Google Season of Docs last year. It didn't work out. It's just one of these things that you have to just sit and do. And we want to completely rewrite a little bit of the documentation, add more documentation, make it more streamlined, and take care of all the small things so that you can compile the documentation yourself very easily. It's a little pain in the ass to compile the documentation right now. But we do it for you so you can get it online. And recently, Nathan pushed a lot, and we got kind of a new governance model, and we got inspired by NumFocus and NumPy on how things are managed in QuTiP. Have a proper board, and have an admin team, have a dev team, and the things that really you can say and do things, and you can run it one-man show or one-woman show, but it doesn't really work in the long run if you have a full ecosystem. So you want something that makes it easy for people to raise their issues. And so we try to come up with a new governance model, and you can go to QuTiP and find the document which tells how this model is going to work, and you can contribute yourself to suggest some changes. QuTiP enhancement policy. Yeah, actually, this is one of the things that came up today in the first board and admin meeting, that we want people to be able to present their own ideas. And we're still finalizing how we can, make that document. But we have a roadmap for development where you can just go and make a PR or suggest new changes and enhancements. And yeah, we are going to participate in Google Summer of Code 2021. Maybe one of the projects could be QuTiP symbolic, or trying to break apart QuTiP control and add new things to it, and so on and so on. So one of the things that I'm really interested in is QuTiP control, because this is of value to experimentalists who really want to control their quantum software. So already what Boxy is doing is one level of it, but then you have a lot of these control algorithms. For example, QuTiP already has this grape and crab algorithm, nice names for them. And then there's also something called Proto, which is built on top of QuTiP for optimal control. And what you really want to do in optimal control is you have this Hamiltonian, and you write, a kind of parameterization like this, where you know what these control Hamiltonians are, and you want to find out what are the best pulses to run to target something. So if you have this Hamiltonian and you evolve it under some noise, what should be these terms so that you can target something that is like a 3-qubit state going to a GHZ state or something like that. So this is very interesting. We want to somehow branch it out, expand it, make it very independent. Then of course I talked about QuTiP QIP, and it has gone beyond kind of simple simulation of quantum circuits. You can add noise at different levels. You can add noise in your control pulse, for example, some white noise, and then you can optimize over these noise and things like that. So we want to make it a bit more rigorous, make it easy, make it streamlined, so that anyone can take it up and use it, and make it as accessible as QuTiP itself to do quantum information processing. So one of the future goals is we want to make a complete unified framework, not just for ideal simulations, but include different kinds of noise. This is one of my pet projects, and I've already found 2 or 3 users of it and using it for some experimental optimizations here. And I've shared it with many experimentalists actually who are very happy to use it, because they don't have to worry about anything. They just do some imports, run the code, and it works. And the idea is basically, there's a Seth Lloyd paper in 2019 that says that you can just use gradient descent to learn unitaries. If you have like a bunch of input and output states, you can use this. So what we try to do is we try to take Google's JAX library, which allows you to implement auto differentiation, and write QuTiP ground up using JAX. And then you can just see that you can take gradients of things, and you can, optimize, launch your stochastic gradient descent algorithm or ADAM or things like that. I think you can even like combine now some neural networks written with JAX with something like QuTiP. You can maybe make a neural network, the output of which goes as a parameter in some Hamiltonian in QuTiP, and try to do these things. So it's very exciting for me because I work on these things, and it has personally made my life very easy to prototype ideas. And the future goal here is we want to make like most of QuTiP auto-differentiable so that you can get better options.
Makes sense.
Yeah, and it's really like it's with quantum machine learning becoming super popular, and it's not popular. I mean, it's a really hype field. Also, you have like neural networks working on quantum systems and quantum neural networks and things like that. Then the heart of it, if you see that the fundamental thing is auto differentiation. If you write differentiable circuits and you can somehow optimize it with gradient descent, you have like a whole bunch of things that you can do. And this is, one of the future goals that I want to make a little bit more prominent and useful for others.
Folks were asking if there's any reason why JAX's NumPy was chosen over TensorFlow or Torch.
Yeah. It's, I personally first went to TensorFlow. When I started, TensorFlow didn't have a lot of complex number support. And then I think one of the Roger Luo, who's contributing a lot to TensorFlow complex numbers. He kind of now added complex numbers to TensorFlow, or he's part of the project that added this. So at that time, PyTorch didn't have complex number support. So then I went to TensorFlow, and it just felt a little bit more complicated, because you have TensorFlow tensors that you need to work with. But here, since QuTiP already had NumPy, like a really nice sync with NumPy, the overhead to jump from NumPy to a JAX NumPy to JAX functions was smaller than TensorFlow. So we chose basically JAX for that reason, and it was a 3-month project. We didn't want to have to do a lot of things, and then of course TensorFlow came up with TensorFlow Quantum. So there's nothing called JAX Quantum. So hopefully we're the JAX Quantum.
There's a +1 on TensorFlow being complicated.
Yeah, TensorFlow 2 still okay. I could never imagine writing what we wrote with JAX with TensorFlow 1, right? So yeah, and we now have a nice little governance model, and anyone can go and contribute to it and suggest changes. So we have an admin team that leads the technical code development, manages things directly. We meet every month once at least, and if we need to discuss more, we meet more often. And this has been really good. Like even if there's not a lot of things to do, it's nice to catch up with the whole team once in a while. And we have like dev teams which are particular projects. Like let's say QuTiP control might have a dev team, and so on. And if someone wants to become a prospective admin team member, they can just send self-candidatures and say, okay, I want to be part of the admin team member. I can contribute this way to QuTiP, and so on. And we can consider it. And then we have like the board, which is kind of people who have more experience and who can kind of get the funding and advise us on things like that. So Will Zhang from Unitary Fund, he's one of the board members. Frank Bernardi, who was there from the beginning, he's one of the board members. And then we have 2 other board members, and you can click them on. So now the thing is like we want to be able to reach out to the community more, and something like this is amazing. Like I think I would want to come to Twitch again just to discuss what new things we can do with QuTiP. People can bitch about things that are wrong with QuTiP, and am I allowed to use that word?
Yeah, there's no rating on this.
Okay. And but then we there's a Google group, and this is kind of the oldest, longest running forum to talk about things related to QuTiP. But you can also post an issue, maybe if you have something specific in QuTiP or a feature request. But we are trying to find out something that works really well and easily so that anyone can come in. And maybe in the future, we are also thinking that if we have these meetings, these admin team meetings, maybe we make these meetings open so that anyone can come or just email us saying, hey, I would like to sit in for the next admin team meeting, give some suggestion or present a new cool idea. And one thing more I think we discussed today actually is if we can combine unitary grants, micro grants, and have like QuTiP projects or things that we would want to do as ideas that people can pick up for micro grants. So that's something that's very interesting.
Yeah, somebody suggested maybe Slack or Discord for QuTiP.
Yeah, I mean, Slack, Discord, a Twitter handle. QuTiP doesn't even have a Twitter handle right now. So
I know, I was trying to find it when I was tweeting today or like promoting the event.
I think it would be a very interesting tool. We have to think about it in the next admin meeting. Posting new ideas and things like that, or it's just a nice way to reach. And I think there's a lot of quantum people on Twitter, so it makes sense to have a Twitter channel. But yeah, Discord or Slack or something. Unitary Fund holds a weekly community calls on MyTech development on Discord. We're not creating any stuff.
That's what I was laughing. Yeah, no, we've had a pretty positive experience. Nathan was referring to there's like we literally just do our kind of weekly stand-ups on Mythic, the project that we develop in the Unitary Labs, just open on our Discord, and we've now gotten like probably 3 to 5 people who join us who are not like kind of the core devs, and they're making PRs and like working with us. It's really nice actually. So it saves a lot of like back and forth async communication to just be like, all right, we're actually in a room together and we can just like discuss this real quick and get a direction. So Will says +1 for community meetings on Discord.
We tried when I joined, I tried Gitter channel and it's still there. Then we tried Slack channel and nothing really ever stuck. So in the end, it was like the best thing was Google Groups and a mailing list, which was working. So yeah, we still have to think about it, and maybe a Twitter channel and a Discord channel maybe would be very nice. Yeah. So this is the last slide, and it's kind of an advertisement to people listening that a question about how to contribute. So one has somewhat functional code implementing a new aspect, but is nowhere near the quality standards. What's a good route to contact the QuTiP team, and if this could be integrated? I think the best way is to open an issue and basically say that, hey, I have this piece of code that does this, and I've reached this much, and link to your code, or maybe just open a pull request. Because a pull request doesn't have to be something which is completely finished, is working, shining, and just ready to be merged. No, you can have like a small piece of code and you just open a pull request and you can kind of discuss more, get comments on your pull request, or you just post it on the Google Groups about a new idea. But I think the fastest way to get noticed would be opening an issue or a PR on QuTiP.
Yeah, the PR functionality that I really like on GitHub is making suggestions. So like, as a maintainer, that's really like that's the easiest way for me to give you feedback on the code, because I can literally make a suggestion as opposed to having to describe it to you, and then you go make the change to the code, and then I validate it.
Exactly. So that would be the best thing. What if a somewhat bigger project would require quite a bit of work? I mean, there are a lot of folks, I think, who have very nice big projects like that they would want to be. I think then you should probably just write an email to one of the admin team members or dev team members that you think would be closest to working on your idea, and then I'm sure we can kind of discuss, have a meeting, and then flesh out a bunch of things that we can do, or make it part of a Google Summer of Code project, or maybe a micro grant. So if you have a really, really big idea, you can just mail to someone on the dev team, and that works. Yeah, and Nathan mentioned that you can email at QuTipAdmin@Google Groups. Yeah, you can do that. Yeah. So the last thing here is actually we have Google Summer of Code 2021. We're trying to participate again. And I just updated the wiki today, so there's not a lot of fresh ideas. So you can suggest new ideas or pick up something from there, and then get in touch with any one of us. And the earlier it is, the better, because we help you kind of craft your proposal, give feedback on how to write your proposal, and show you how last year's proposals were. So we try to do the best to make a successful application for you. So try to get in touch with us and have a look at the wiki page. And another thing is, my former supervisor, Franco, he mentioned that he has a bunch of postdoc opportunities for people who want to kind of work on QuTiP or do something with QuTiP. So if someone who wants to get full-time involved with QuTiP, and the position is based in Japan, so you have to actually go to Japan. So if you want to go have some ramen and contribute to QuTiP and have the skills, then we're going to make, I think, a post on QuanTiki soon, and you'll hear from it, or just write to me or Nathan, for example, and we can get back in touch with you. So
we'll make sure to post it on the Unitary Fund Discord and stuff too. So
yeah. So yeah, that's it. Thank you.
So first of all, thank you so much for a great talk, Shahnawaz. I think this was a great introduction into, there's tons of stuff here even that I didn't know about QuTiP. And so, yeah, I want to especially invite Chad, if you have any other questions for Shahnawaz, please put them in chat. But I had kind of just a more general question for you, if you still have time.
Yeah, I have time. It's 7 in the evening, so
that's right. Fair.
More meetings.
It's time for quantum beers or whatever. So you've kind of illustrated with a lot of the stories and anecdotes you shared here of a lot of people, like even yourself, you just saw the advert and were like, hey, can I help out with this project? What are, you've mentioned this postdoc opportunity, are there other ways, if I was either a student or somewhere along the education spectrum, or even just a developer with no quantum background whatsoever, where do you think they could kind of plug into the QuTiP team? I guess there's the governance team or whatever, but do you have labeled good first issues, or what are the entry points, I guess?
Yeah, I mean, we tried to do that. One of the entry point, I would say, we're trying to make, this page of ideas. And I think, right now the page of ideas is becoming Google Summer of Code 2021 page. But one of the things probably, and this is completely on us, that we have not yet tried to kind of tap into the wider community of developers, because there are some amazing developers out there who not necessarily come from a background of quantum physics, but can really help us in many ways. So we will try to kind of have a list of ideas and put in a mix of things that requires you to have a little bit of quantum background and someone who's completely fresh. And then at the same time, I suppose having good first issues there is a nice thing. We have it for GSOC, so let's see. I'll try to make more labels like that. And I guess you could just write to one of us or open an issue if you have some small piece of code that you work with at this point, and just join the team.
Are there from thinking about the seasoned developer angle here, are there any big pain points for you in the CI, or you kind of mentioned the documentation build process is a little hairy? Are there any of those areas there that you're if we could magically have someone help us, what would be of most value to you?
Yeah, definitely. I mean, right now, setting up the documentation or kind of rehauling the documentation, one of the problems that we have is in the documentation, we have these IPython kernels used in Sphinx, which runs the code, and then somewhere the code breaks and you have to rewrite this so it doesn't render properly. So what personally I want to do is change everything to Sphinx Gallery, and I kind of know how to do it. It's just the time that I need to put in is not coming up. So that's one big thing. Like we want to completely make it so that you just write markdown text, for example, and that gets picked up, or maybe RST text and that gets picked up. And then the code, for example, you write all examples not as notebooks, but as Python codes with kind of commented explanation sections. And it gets picked up by Sphinx Gallery, run automatically, renders the plots, and places it nicely. So that's, of course, one point. Another point that has been going on for almost many years is multiprocessing. So multi-threading, multiprocessing in QuTiP is kind of a pain in the ass again, and none of us have been able to kind of work around and figure it out. So there is some MPI capabilities, and you can compile it, to run on a cluster and things like that. But if you just want to use on your laptop some multiprocessing, it's not so clear how to do it. Another thing is, I think if someone who's very, very knowledgeable about using GPUs in the backend. So I have in my group, for example, some very seasoned GPU users. They have taken inspiration from QuTiP and written very efficient GPU code to, kind of simulate these things, run swarm optimization and things like that. So if there are like these things that someone can make QuTiP faster, better on GPUs, that would be really cool. So yeah.
Nice. Cool. Well, I think we might have time for one more question. Thanks, Pradesh, for the follow. So knowing what you know now, you've spent quite a bit of time working on this project and quantum stuff in general. Like, if you could go back in time and like teach yourself one thing or like kind of one topic, what would that be? That you think would kind of save you a lot of time in your process here?
I would say, like, I had a really zigzag way of learning these things. So I mean, I had a physics degree. Yeah, I know you do basic quantum mechanics 2, Sakurai, and then you do like quantum information courses, and you learn about qubits and stuff like that. But the real learning that happened and that I really had to pick up on my own was learning about open quantum systems, master equations. How does this thing work when you take kind of the nice idealization of unitary evolution out of the picture? I mean, Unitary Fund's motto is because evolution is unitary, but I would say that you really have to learn about open quantum systems properly to get into the cutting edge research stuff. And if I had a chance, maybe already towards the end of my undergraduate, I would go read Ahsan Nazir's notes on open quantum systems and basically try to understand how to run open quantum systems and understand, whatever was required to know what's the Liouvillean, what's the Lindbladian, how do you simulate a qubit interacting with an environment and things like that. So that's something that I would teach myself in, I don't know, 2015, 2016 when I started this, because it took me a long time to reach the level where I really understand it now.
Are there any like non-quantum physics related things, like in terms of like open source tools, or like is there a dev tool that you use like on a daily basis that you're like, I can't do what I do without it? It could be like an IDE or a command line tool, or just your favorite terminal. Like, what do you like to use?
Sublime Text.
Gotcha.
I tried Vim, Emacs. It's like some of my older cool coder friends. I see their terminal, they're doing super cool stuff. But in the end, Sublime Text serves the purpose for me, and it's been really good. And another thing is, everything that I know about open source, I kind of learned because of my own Google Summer of Code project, which was not on quantum. And I had a really good mentor, Ariel Rohim, from University of Washington Center for Data Science, who taught me everything. And at that time, I didn't even know how to use Git properly. So I would say, two things that's really, really useful if you are into it. Go to try.github.io and just learn how to use Git. You just need to learn a few basic things and you can get started. And that's one thing. And the second thing that I really, really would say change how I code is testing. Once my supervisor during the GSOC meeting, he saw that my code was not tested and he didn't even want to continue the meeting. He said, like, untested code is broken code. So finish writing the test first, and making sure everything is okay, and then we'll speak. So if I had learned proper testing before and Git before, I would have been far ahead in this journey right now. So that's something that someone who's new should definitely look at.
Sweet. Yeah, I wish I would have learned better testing sooner too. It's always kind of like documentation. You're excited about writing the new feature, you like jump into doing that first, and then you're like, oh yeah, I got to go back and do that other stuff.
Yeah.
Cool. Well, yeah. Oh, I think Jake says Eric's been working on getting low-key parallelization working recently, which hopefully, or LOKY, I don't know what that, which hopefully will make multi-processed parallelization a little bit easier, especially on Mac and Windows. So,
yeah,
yay for cross-platform functionality. Cool. Well, thank you so much again for joining us today. This was really fun to kind of learn about a tool that at least I was already a little bit familiar with, but there was so much more to it that I hadn't really experienced because they weren't things that I necessarily had done, but now I know it can do. So yeah, if anybody is interested in getting in touch with the QuTiP project, we've mentioned a lot of different ways: file an issue, email the devs, Google groups, like you got a lot of options, whatever works for you. And I'll put a project, if you need just a link to the basic QuTiP repo there, or QuTiP website. And yeah, we look forward to seeing everybody for our next quantum software talk. Thanks everybody. Have a good one.
Thank you, Sarah. Yeah.